Life is full of choices. Should I eat the cookies or drink the water? Or should I eat the cookies and drink the water? Or maybe I don't eat the cookies even or if I spill the water. Sounds confusing. That's the magic of logical connective.
Don't worry, I'll help you connect the dots logically, of course. Welcome to the Logical Connectives, where life, logic, and cookies all make sense eventually.
Hi, my name is Nusha Raja binti Hilmi.
Hi, my name is Siti Nunadatul Husna binti Samuri. Hi, my name is Nur Iman Humaira binti Muhammad Faizan. Hi, my name is Fitri Mansafia binti Aizam.
Hi everyone, let's go to the introduction. Logic helps us evaluate arguments, make decisions, and understand how statements interact with each other. At its core, symbolic logic is about the use of statements often represented by letters like P, Q, or T, and the logical connections between them. A proposition or statement in logic is always either true or false, but never both at the same time. This is a foundational principle that enables logical reasoning. When we talk about the truth value of a statement, we mean whether the statement is true or false. For example, consider the statement, "It is raining." The truth value depends entirely on the actual weather conditions. By using letters to represent statements, logic becomes a structured way to analyze ideas clearly and objectively.
Now, I'm going to explain about true values and truth table. So, what is true values? A true value is whether a statement is true or false. A truth table shows all possible outcomes of a logical expression based on different input values. It helps us to see how true or false values combine using logical operations.
What is conjunction? Conjunction is the logical connective used to combine two propositions such that the resulting statement is true if and only if both proposition is true. The truth condition for conjunction is the truth of P and Q depends on the truth value of P and Q. It is true if only if both P and Q are true, and it is false if either P or Q is false or both are false. For the conjunction truth table, when P is true and Q is true, the statement P and Q is true. Next, when P is true and Q is false, the statement P and Q is false. When P is false and Q is true, the statement P and Q is false. And lastly, when P is false and Q is false, the statement P and Q is false. For example, given P, it is raining, and Q, I'm carrying an umbrella, the conjunction of P and Q means it is raining and I'm carrying an umbrella. The statement is true only if both of the proposition is true. So, if either one of the proposition is false, the whole statement will be false. What is disjunction? Disjunction or combines two statements resulting the statement to be true if at least one of the component is true. Truth condition for or depends on the true value of P and Q. The result is true if either P or Q or both are true, and the result is false only when both P and Q are false. For the truth table, when P is true and Q is true, the statement P or Q is true. Next, when P is true and Q is false, the statement P or Q is true. When P is false and Q is true, the statement P or Q is true. And lastly, when P is false and Q is false, the statement P or Q is false. For example, given P, I will take the early flight, and given Q, I will take the evening flight. the disjunction of P or Q means I will take the early flight or I will take the evening flight. The statement is true if one or both of the proposition is true, and the statement is false only if both of the proposition is false.
Now, let's explore negation, a fundamental concept in logic. The negation of a statement is the reversal of its truth value. If a statement is true, its negation is false, and vice versa. For example, if the statement Mark is popular is true, then its negation Mark is not popular would be false. We symbolize negation using this symbol, and we interpret it as not. For instance, negate P means not P. To make this clearer, we use a truth table. When P is true, negate P is false, and when P is false, negate P is true. This systematic approach ensures that every logical operation has a clear and consistent interpretation. Negation is crucial because it allows us to consider alternative perspectives and explore the opposite of any given statement. This logical operation will become even more significant as we examine more complex structures like conditional statements. Now, let's discuss conditional statements, another key concept in logic. A conditional statement connects two propositions, often phrased if P then Q. Here, P is the condition and Q is the result. For example, if Mark studies hard, then he will pass his exams. In logic, we symbolize conditional statements as P implies Q. This can also be expressed in various forms such as P implies Q, Q is necessary for P, or P is sufficient for Q. This variation reflects the relationship between the two statements. The truth value of a conditional statement follows this rule. If P is true and Q is false, the conditional statement is false. In all other cases, the conditional statement is true. For instance, if Mark studies hard, P is true, but still fails, Q is false. The statement, if Mark studies hard, then he will pass his exams, would be false. Understanding conditionals helps us analyze cause and effect relationships and build sound arguments. Together with negation, this forms a strong foundation for logical reasoning.
Biconditional. A biconditional is a logical connective that joins two statements to form an if and only if statement. Biconditional statement is represented by P if and only if Q. A biconditional statement is true if both P and Q are either true or false. A biconditional statement is false if one is true and the other is false. For example, number 1, a polygon has 4 sides if and only if it is a quadrilateral. Number 2, you will pass the test if and only if you score at least 50%. For a biconditional truth table, if P is true and Q is true, then the statement is true. If P true but Q is false, then the statement is false. If P is false but Q is true, then the statement is false. If P is false and Q is false, then the statement is true. Example 1. Write down by using the proposition symbol to represent each of the following primary statements. P. Damon is rich boy. Q. Damon live in bungalow house. R. Damon is stingy. A. Damon is a rich man and live in bungalow house. B. It is not true that Damon is a rich man and stingy. C. If Damon lives in bungalow house, then he is rich. D. Damon is rich man but not stingy. E. Damon is a rich man and live in bungalow house and he is not stingy. Solution A. Damon is a rich man and live in bungalow house. P and Q. B. It is not true that Damon is a rich man and stingy. Not in bracket P and R. C. If Damon live in bungalow house, then he is rich. Q implies P. D. Damon is rich man but not stingy. P or not R. E. Damon is a rich man and live in bungalow house and he is not stingy. P and Q and not R.
Next is example 2. Example 2 is from symbol to sentences. So the question is, let P, Q, and R be primitive statements denoted as follows. So for P, Lily goes for a morning run. Q, Lily eats a healthy breakfast. And for R, Lily feels energetic throughout the day. First question, the symbol is N. So we have to combine the two primitive statements for P and Q. So for P is Lily goes for a morning run, and for Q eats a healthy breakfast. So we have to combine it. It become Lily goes for a morning run and eats a healthy breakfast. For the second question is combination of conjunction and conditional. So when we combine it, it will become if Lily goes for a morning run and eats a healthy breakfast, then she feels energetic throughout the day. For the last question is combination of negation and biconditional. So the symbol is not Q if and only if R. So the answer is Lily did not go for a morning run if and only if she feels energetic throughout the day. Here is the example 3. We are solving a logic problem. So the statement is a combination of logical expression and we need to find the true values of P and Q. Given that R is false and the whole statement is true. So the statement is P implies to Q and P equivalent to R, and not Q implies to P or P. Okay, so for the first step, we are going to put the statement into a column for each of symbols. So we are going to do two columns, one for symbol and one for the true value. So why we make it like this? Because it's easier for us to see the true value for each symbols. So next, we are going to break it into smaller parts. So for the first part is P implies to Q. So this means if P is true, then Q must also be true. Since P equals to false, this is automatically true because false can make the statement wrong. For the second part is P is equivalent to R. So this means P and R must have the same true value. So R is equals to false, so P must also be false to match. So for the next part is not Q implies to P. So this means if Q is false, then P must be true. But Q equals to true, so this part doesn't matter because not Q equals to false, which makes the statement automatically true. For the last part is not Q implies to P or P. This is an OR statement, so at least one part must be true. Since we know that not Q implies to P is true, so this whole part is true. Lastly, we have to combine the results. Now let's put it all together. For the first part is P implies to Q and P is equivalent to R is true. And for the second part, not Q implies to R or P is also true. The value that make the whole statement true are P equals to false, Q is equal to true, R is equal to false. To summarize, we solve this step by step, checking each part of the statements. This shows how we can use logic to find the true values.
Conclusion: using symbols to stand for relationship between statements. Logical connective, we learn first, conjunction and disjunction or negation, not conditional, P implies Q, biconditional, P if and only if Q. A statement is a sentence that can be either true or false.
Bye! Thank you for watching!